Hello everyone, thanks for coming. Today we are going to do a review of our week 10's lectures. So in this week, we talk about the cylindrical coordinates for 3D space, the spherical coordinate for 3D space, as well as linear integrals. So for a point in space, given the rectangular coordinate x, y, z, the cylindrical coordinate is r, theta, z, which equals to square root of x squared plus y squared arctangent y over x, z. So we can see that we are doing a polar coordinate for the first two dimensions x and y and keep z fixed. Similarly, given the cylindrical coordinate r, theta, z, the rectangular coordinate is r cosine theta, r sine theta, z. If we are doing integrations, the change of variables tells us that dx, dy, dz equals to r, dr, d theta, dz. Don't forget r here. This r comes from the polar coordinate transform. Then we talk about the spherical coordinate. So for the spherical coordinate, we need to transform all of the three variables x, y, and z. For a point in space r cubic, given the rectangular coordinate x, y, z, the spherical coordinate rho, theta, phi is defined as square root of x squared plus y squared plus z squared for rho, which is the distance from the origin to the point, arctangent y over x, and then arc cosine z over x squared square root of x squared plus y squared plus z squared. Phi basically is the angle between the line segment OP from the origin to the point as the positive z-axis. Similarly, given the spherical coordinate rho, theta, phi, the rectangular coordinate is given as rho cosine theta sine phi, rho sine theta sine phi, rho cosine theta. If we are doing integration, the change of variable rule gives us dx dy dz equals to rho squared sine phi d rho d theta d phi. So don't forget this rho squared sine phi here. Then we talk about vector fields in space. For 2D vector fields on R squared, it is a function capital F that assigns to each point x, y a two-dimensional vector, capital F of x and y. Similarly, for 3D vector fields on R cubic, it is a function capital F such that it assigns to each point x, y, and z a three-dimensional vector, capital F of x, y, and z. Specifically, the vector field is called a conservative vector field if capital F is the gradient of a function f of x and y in the 2D case or f of x, y, and z in the 3D case. Finally, we define linear integrals on smooth curves. Suppose we can parameterize a smooth curve as c equals to xt, yt, where t ranges from a to b. For a continuous function, small f, the linear integral on the curve with respect to the length of the curve is defined as integrating from a to b f xy times square root of x prime squared plus y prime squared. So this term quantifies the length of the curve with respect to the unit length of the curve with respect to the parameter t. Similarly, we can define a linear integral in x dimension that is integrating from a to b f times x prime. We also have the linear integral in the y dimension, integrating from a to b f times y prime t dt. Finally, for our vector field, we can define the linear integral of the vector field on the curve C. The defining formula is integrating from a to b f of xt, yt times here the inner product of the vector field f and the derivative of the curve with respect to the parameter t, that is r prime, which is x prime and y prime dt. Thanks for listening.